Hi there, Mr. Sutton here with the IM3 8-3 Extra Practice number 3 solutions on theoretical probability. For this problem, we want the probability of drawing a red card out of a deck of 52. So we have 52 total possible outcomes for the whole deck, and there are always half of the cards are going to be red and half are black. So that's 26 out of 52 that are desired outcomes, and then as we said, that can reduce to 1/2. On this one, we want the probability of drawing the cards 3 through 4 from a deck of 52. So we have 52 total outcomes, and then there's 4 of each of these, 4 for each suit. So we have 4 of the 3s, 4 of the 4s, that's a total of 8, and that reduces to 2/13. For this one, given a single die, we want the probability of rolling a 3 or smaller. So total possible outcomes here is going to be 6, the numbers 1 through 6. And out of those numbers, there are 1, 2, 3 numbers that are 3 or smaller, 1, 2, and 3. So that's 3 out of 6 then, which reduces to 1/2. For this one, we want the probability of rolling factors of 120 on a single die. So we have 6 total possible outcomes. And out of the numbers 1 through 6, how many are factors of 120? Well, certainly 1 is, 2 also because 120 is even, 3 is a factor because the digits of 120 add up to 3, and 4 is a factor because 4 goes into 20 and 100, 5 is a factor because this ends with 0, and 6 is a factor because 2 and 3 are both factors. So that tells us that all 6 of these are desired outcomes, which we can reduce then. 6/6 is just 1. On this problem, using this spinner here, we want to know if we have an equal chance of landing on either 1 or 4. So we have to calculate the probability of each case and then compare them. So in both cases, we're going to have a total number of outcomes that's 11, if the number of spaces if you count them out here. So let's do probability of 1 first. So that's going to be something over 11. Now how many 1s do we have on here? We have 1, 2, 3, 4, 5 desired outcomes, 5 1s, so that's 5/11. For the probability of 4, that's again going to be something over 11 because we had 11 total spaces. For the 4s, we've got a 4 here, another one up here, and it looks like those are the only 2. So 2 out of 11. Well, since 5/11 does not equal 2/11, that means we do not have an equal chance of landing on either of those spots. For this problem, we want to know if we have an equal chance of landing on 3 or 4. So let's calculate the probability of each one individually and then compare them. So for probability of 3, well, we know that there's, if you count these spaces here, 11 total outcomes. So that's something over 11. And how many of those are actually 3s? Going through here, it looks like there's only a single 3, so that's 1/11. Now for the probability of a 4, again, we have something over 11. And for 4s, we have 1, 2 of them here, so that's 2/11. So although these are pretty close, 1/11 and 2/11 are not the same number. So this is a no, we do not have the equal chance of landing on either of those numbers. On this problem, we want the probability of this spinner here not landing on 2 or 3. All right, well, we know that there's 11 spaces if we count them here, so it's going to be something over 11. And then let's just count up the spaces that are not 2s or 3s. And actually, there's not a whole lot of 2s or 3s out there, so it might be faster to count the ones that are 2s and 3s and then subtract that from 11. So let's see here. We've got a 2, a 3, a 2, another 2. So that's 4 total that are undesirable. So subtracting that from 11, that means there are 7 numbers that are not 2 or 3, that are not undesirable. So that is our probability. For this problem, using this spinner down here, we want to know the probability of not landing on A. So there's 8 spaces total here, each with an equal area, so that's 8 for the total possibilities. And the probability of not A, well, there's only a couple A's on there, so it's actually probably faster to find the spaces that would give you an A and then subtract that from the total of 8. So we have 1 A over here, here's a second A, and that's it. So that means that 8 minus 2 gives us 6 spots that are not A. And we can reduce 6/8 to 3/4. For this one, we want the probability of our spinner landing on A or C. So we have 8 possibilities total, And how many are A's or C's? Well, there's 2 A's and there's a C, so that's 3 out of 8 total. For this one, we want the probability of not landing on E. Okay, well, there's 8 possibilities because there's 8 spaces on this spinner. And let's see, 4 of them are E's, 4 of them are not E's. And they're pretty clustered together, so they're easy to pick out. So that's 4 out of 8 chance of not getting an E, which we can reduce to 1/2. For number 5, we're given a table with all the possible results from rolling 2 6-sided dice. So in other words, the possible sums of those 2 numbers. So if you roll a 1 and a 1, you could get a 2. That's the lowest you can get. If you rolled 2 6s, you could get a 12. That's the highest you can get. And you can get everything in between 2 and 12. We want to complete the table to find the theoretical probability of rolling each of these sums. So this will be a decent amount of work because we have to count up the ways to roll each of these sums and then turn it into a probability. Let's start with the easiest one, rolling a 2. There's only one way to do that. That's if you roll a 1 and a 1. And I'm going to be referring us back to this table from the 7-3 lesson here. So we've got a 1 and a 1. That'll give us a 2. So there's one way to roll a sum of 2. So that's a 1 out of 36 probability. And we know it's 36 because there are 6 possible outcomes for each dice roll. So 6 times 6 gives us 36. All right, rolling a 3. So we've got, if we look back at our table here, we've got a 1 and a 2 or a 2 and a 1. That's 2 different ways to do it. And 2 over 36 reduces to 1 over 18. Rolling a sum of 4, you could do a 1 and a 3, a 2 and a 2, a 3 and a 1. So that's 3 different ways to do that. 3 out of 36 is going to be 1 out of 12. Rolling a 5, back at the table. We've got a 1 and a 4, a 2 and a 3, a 3 and a 2, a 4 and a 1. So that's 4 different ways, which gives us 4 out of 36, or 1/9. And in case you were wondering, yes, there is a pattern here. For every number you go up, there's one more way to roll that number. So the next thing is 5, which becomes 5 out of 36. And to roll a 7, so for this one, that's going to be 6, because if we look at our table, we could do a 1 and a 6, a 2 and a 5, and so on and so forth. This whole diagonal with 6 possibilities on it. And 6 out of 36 is 1 out of 6. Now, when we get to 8, things start going down again. If you look back at this table, to roll an 8, you could do a 2 and a 6, 3 and a 5, 4, 4, 5, 3, and 6 and a 2. So that's back down to 5 possibilities. So 5 out of 36. And with 9, as our numbers get higher, there's less and less ways to roll it. So this is down to 4 again. So that's, again, 1 out of 9. 10 is down to 3, so 1/12. 11, well, you either need a 5 and a 6 or a 6 and a 5, so 2 different ways, 1 out of 18. And then to get a 12, again, you need 2 6s. There's only one way to do that, so that's 1 out of 36. Follow-up question. In the game of craps, which they play at casinos, for part of the game, everyone loses all their money when someone rolls a 7. Why do you think the game makers chose 7 to be the money-losing roll for this? Take a look at our table here. So we have the highest probability of rolling a 7. There's more ways to roll a 7 than any other roll. So this is probably why they chose 7 as that number, because they like people to lose their money.